Good day and welcome to our example video on the topic of the flat plate convection via the empirical method of solutions. So here we have an example. Consider atmospheric air at 20 degrees Celsius and a velocity of 30 meters per second, flowing over both surfaces at a 1 meter long flat plate that is maintained at 130 degrees Celsius. The question is to determine the rate of heat transfer per unit width from the plate for the values of critical Reynolds number corresponding to the following values. So we are going to have a plate that is 1 meter long and air is blowing over both sides, so here and here. Both are at 30 meters per second and at 20 degrees Celsius, and temperature of the surface Ts is equivalent to 130 degrees Celsius. So now we are going to solve for the heat rate per unit width of the convection transfer across the surface. So starting with our solution, we need to first calculate for the Nusselt number. In order to calculate for the Nusselt number, we need our Reynolds number and our Prandtl number. Both of these numbers can be calculated using, of course, first data from our appendix 8.4. This is from your textbook appendix, and what we know is we need to use our film temperature in between the temperature of the surface and temperature of the fluid. This translates to 85 degrees Celsius, or when moved to Kelvin is 358 Kelvin. From our data table, we know that there is 350 and 400 available. That is why we need to interpolate our data in order to get the most accurate results. So here we have our density, our absolute viscosity, and our thermal conductivity, as well as our Prandtl number. So from here, we need to calculate our Reynolds number, and our Reynolds number that we need to calculate is at the end of the plate at length L. So we will need to input our density multiplied by our velocity multiplied by the length of the plate divided by the absolute viscosity. The problem made mention, however, three different critical values, which are 100,000, 500,000, and 1 million, or 1 times 10 to the raised to the power of 6. So from here, we will use our corresponding C, M, and N values for our Nusselt equation, and this is unique to the geometry and the flow condition. Upon checking our plate, we know that initially it starts as laminar flow and then transforms into turbulent flow. Therefore, we will need to use a Nusselt equation that is for the mixed flow of laminar and turbulent. So this corresponds to the use of a certain Reynolds number Re sub L, or the Reynolds number at the end of the plate, which has been already computed here. This value, 1,381,895. And also specific critical Reynolds numbers, which will be used for this particular constant A, which will be plugged in this portion of the equation. We already know our Prandtl number from our table, which is already given here. So first, let's apply this to a critical Reynolds number of 100,000. So using the formula, A is equal to this following expression. Substituting 100,000 for these Re, Reynolds number sub C, substituting 100,000 for each will give us a corresponding value of 160.0248. Next, we use this A value for our Nusselt equation. So we plug that in to our equation right here. Plug in our Reynolds number sub L and our Prandtl number. evaluate our equation, and we will be left with a Nusselt number equivalent to 2,540.997, or you can round it off to 2,541. From the Nusselt number that we've just calculated, we can use this expression, the very definition of the Nusselt number, which is the ratio of the convection over the conduction of the fluid. So from here, we only need our conduction K, which is given to be this value right here, 30.608 multiplied by 10 raised to the power of negative 3, which translates to this decimal value. Plug this in. Plug in our value for x, which is for this specific geometry, 1 meter. And we will be left with our value for the average convection coefficient, which is equivalent to 77.77 watts per square meter. From here, we can use this average convection coefficient for our heat rate, equivalent to h bar multiplied by the area multiplied by the temperature gradient. And since the problem is asking us for a per width analysis, so we divide our area, we rewrite this area as width times length, and Q over width is equal to h bar multiplied by our length multiplied by our 150 minus 20. So from here, we input our average convection coefficient, we input our length, and we input our temperature gradient, which will give us this value right here. So our value, the total heat transfer across the plate per width, is equivalent to 10 kilowatts, almost 10.11 kilowatts per meter. Now, the problem also made mention that there are different cases for the critical Reynolds number. So how does this take place across the different solutions? So again, we go back to our A, since this is the variable that is affected by different values for our critical Reynolds number, we go back to this point in our solution. So from here, this will give us two different values for A, which corresponds to substituting the corresponding critical Reynolds number. Here we substitute 500,000. Also here we substitute 500,000. Here we substitute 1 million. And here we substitute 1 million also. This will give us these different values. Now again, these different values will be plugged in to our Nusselt number equation here and here. These will give us two different Nusselt numbers, 1909 and 1200. So same process, use the same K since our K is not a function of the critical Reynolds number but only as a function of temperature of the fluid. So we will use the same K, we will use the same characteristic length, 1 meter, and now we will be left with two different values for the average convection coefficient. One at 58.45 and one at 36.75. Plugging in these different values to our heat equation, and we will be left with our new values for our heat rate. Now, as you can see, we have a trend here with increasing critical Reynolds number. We see a result of a decreasing amount of heat rate. Why is this so? So if we take a look at the boundary layer of, if we remember from our previous lecture, our average heat transfer, our local heat transfer, changes with respect to the type of flow. So here we have a laminar flow that starts to begin. This is the boundary layer. This is the convection coefficient. So as we can see here, at a small boundary layer, we have a high value for convection coefficient. But as we move across the plate and the boundary layer gets larger and larger, our temperature gradient also becomes lower and lower, thus giving us a lower convection coefficient. this lower convection coefficient maintains this trend until it reaches the critical zone. So up until it reaches the critical zone, the value of the convection coefficient is very low. After this, we see a spike since eddies will now be forming and mixing of the fluid will now be better in comparison to the laminar flow. We see a spike in convection coefficient. And again, the same trend as we move towards an increasing boundary layer, we see another downward trend for our convection coefficient. Now, how does that translate to the varying critical Reynolds numbers? So the varying critical Reynolds numbers moves this critical region towards the right. So as we can see here, our initial critical region is located around here. But if our critical Reynolds region is larger, we will have to move lower across the plate and up lower as we go larger. This in turn will give us a small value for our H here, another small value for H, small value for H, while here we have a higher value for H, a higher value for H, higher value for H. So of course, in proportion to the amount of surface area these high and low convection coefficients have, this will reflect in terms to your total heat rate, which we can see here. If we were to put our values here, this is the 10 kilowatts per meter. This is the 7.6 kilowatts per meter. And this is the 4.77 kilowatts per meter. Now, this is not to scale. This is obviously not to scale since we do not have exact dimensions here. But I would just like to emphasize this point right here. So thank you for listening to this short demonstration of how to use the empirical formula for flat plates.